Okay, so good morning, anyone who's joined so far. So this morning we just have Brien Nolan here, who is the program chair of our MSc in Astrophysics and Relativity. Um, he's going to give an overview of the whole program, and then at the end we will have a chance for you guys to ask any questions that you have. So there is a Q&A option at the bottom of the screen. So you can put your questions in there as we go. And then at the end, we will come and answer any questions that we do have. So Breen, I'll hand it over to you and you can take us away.
Right, thanks very much, Frank. So as Frank says, my name's Brien Nolan, Professor Brien Nolan. I'm currently the head of school in the School of Mathematical Sciences, but more importantly, I'm the chair of this master's program, the MSc in Astrophysics and Relativity. So the way we're going to proceed this morning, I'm going to go through a presentation that fills in some of the detail about the program. And as Frank says, if you have any questions, you can pop them in the Q&A as I'm going along. And we'll play it by ear. I might answer the questions as they pop up, or we can come back at the end to go over them. So let me just share my screen here and I'll get started on this presentation. Okay, so I guess that's visible there, Frank. Is it okay?
Yeah, we can see them, yeah.
Okay, very good. Okay, so I suppose a little bit of admin detail. The program is called the MSc in Astrophysics and Relativity. This has the course code MSAR, MSAR, and if you're looking online, you should be Googling DC742 to find the program, web pages, and that's a code that you would need to submit an application. So, as I said, I'm Professor Brien Nolan. I'm a member of the Centre for Astrophysics and Relativity, CFAR, and also a member of the School of Mathematical Sciences here in the university. Okay, so here's a table of contents for what I'll be doing. Um, Delighted to have you here. Listen to the presentation. I'll give an overview of what the course is about and then go into a bit more detail about program structure and content. I'll talk about the program requirements, what kind of students would be eligible to enter onto the program, and what career and research opportunities stem from the program. I thought I'd start off with a quick overview, trying to answer the question really, well, why did we set up this program? It's only been running for a few years. We'd be going into our fifth year in September. But I suppose really where the program came from is the fact that, well, this is really a very exciting time in the worlds of astrophysics and relativity. There's lots of new data available, lots of interesting discoveries and detections that have been made over the last, well, I suppose heading for nearly 10 years now. I suppose the first of these that come to mind is the detection of gravitational waves by LIGO, the Laser Interferometer Gravitational Observatory. This was done in 2015, and the team was awarded a Nobel Prize in 2017. There are also fascinating discoveries being made about black holes. I'm sure you've seen the images of the black holes in the galaxy M87. And this settled a lot of questions about the nature of black holes. And indeed, there was another Nobel Prize awarded for those discoveries in 2020. There are new telescopes, either now on stream or coming on screen. The ILOFAR, that's the Irish version of LOFAR, the Athena telescope, and the Cherenkov telescopic array. There's also new data from existing experiments like the James Webb Space Telescope and the DESI experiment, which is discovering new facts about the early universe. So researchers in DECU Centre for Astrophysics and Relativity, we came together to offer the new MSc program on these cutting edge areas. And from the very beginning, we had two aims in mind. On the one hand, to give opportunities to students to study this really exciting, this really cool science. And then on the other hand, to build up excellent employability skills. And that's the theme that runs throughout the program and that will run throughout my presentation. Okay, so that's where the program came from. This team of people, researchers working in this area, wanting, I suppose, to train more students in this area that they can enter into it as well. The program structure, it's either 1 year full-time or 2 years part-time, this MSc program. So 1 year means 12 months, running from September to August. It's a 90 credit program and the European credit transfer system. And overall, I suppose the main structure to bear in mind is that there's two teaching semesters. First semester running September to December, where you do 30 credits of courses, you attend classes, lectures, tutorials, carry out assignments, and do exams before Christmas. Semester two runs January to April. Again, 30 credits. So you attend classes, lectures, tutorials, labs, carry out various kinds of assignments, and do your exams. And then what I think in some ways is the most interesting part of the program is the summer project that students undertake on an individual basis, meaning that you have individual supervision with one of the researchers in the Centre for Astrophysics and Relativity. And this is a third of the program, 30 credits. I'll say a few more words about the project in a few moments. Okay, well, what will you be learning? I'll say a few words about the part-time structure after I talk about the content of the program. So the content is structured over three pillars. It's an MSc in Astrophysics and Relativity. So the two key pillars really are, of course, astrophysics and general relativity. And they're supported by a third pillar, which we refer to as the computation and data analysis pillar. So that summarizes the content. It's across these three areas, uh, not distinct, but overlapping in various different ways. On the general relativity pillar, there's three modules that you'll take. In semester one, there's an advanced introduction to general relativity, and that means if you're studying general relativity, you have to have some mathematical background, and the relevant mathematical background goes by the name of differential geometry. So that's our semester one module under that heading. And then in semester two, well, really it's more about the applications of the theory of Einstein's theory of general relativity to the study of black holes and of gravitational waves. So in black holes, studying the formation, studying dynamics, studying mathematical properties, studying quantum properties of black holes, including the famous Hawking radiation. In the gravitational waves module, you'll study the formation, generation, propagation, and detection of gravitational waves, so the whole spectrum. On the astrophysics pillar, under the astrophysics pillar, three modules again. Semester one, advanced introduction to theoretical astrophysics, where you're looking at various different things, often linked by the theme of star formation. So it's the fundamental of astrophysics, I suppose. Astrophysics being the physics of stars. So a lot of material about star formation, paying particular attention to the role of plasmas and magnetic fields, looking at astrophysical jets, looking at the stellar lifespan. In semester two, then, there's the more advanced modules, one on extragalactic astrophysics, bringing us up to cosmological scales, looking at the intergalactic medium, galactic formation and galactic dynamics. And then under high energy astrophysics, looking at some of the most energetic events in the universe. So this will be studying things like pulsars, gamma ray bursts, looking at how the processes that drive the formation of these objects proceed, and how we can detect and those 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 how we can detect those events, the formation of gamma ray bursts, and how we can understand the data that are observed and interpret the physics of what's going on. Okay, so the third leg is the computation and data analysis pillar. And there again, it's three modules, this time two that take place in semester one. And here you will be doing modules that very much answer to that brief we have in the program to develop students' employability skills, to equip them with transferable skills that have applications in a huge variety of areas. So partial differential equations are, well, I suppose this is a maths module, and this is the branch of mathematics that's in some sense used to describe systems that have moving parts, in some sense. So differential equations involves the study of quantities that are changing over time. Partial differential equations typically involve the study of systems that are changing over space and over time as well. And that's exactly the kind of thing that we have in the astrophysical setting. We have a semester one module on data science and machine learning. These ideas, of course, being extremely important in almost all areas of industry and enterprise and research. We're in the era of big data, and this module will help you to deal with that big data and learn some AI techniques, in particular the advanced statistical techniques involved in machine learning to analyze and interpret the data. In the second semester, we have a very interesting module on high performance computing. Um, so there is a computational element across, I suppose, nearly all of the modules, especially the astrophysics modules, where there's some data analysis required, and there's some computational physics involved there as well. So in the high performance computing and quantum computing module, it's about taking those computational skills really to the next level. So high performance computing is the kind of computing that's required to analyze astrophysical systems, and to crunch the data for those systems as they apply to the real world. So on a standard desktop computer, there simply isn't enough capacity to analyze, let's say, the evolution of stars or the emission of gravitational waves from colliding black holes. We need what's known as high performance computing, where we link up lots of different processors together and learn how to write computer code that can be distributed across those different processors, and so leverage the capacity of high scale computational power. Quantum computing, much newer area, but again, it's the same idea, I suppose, in some sense, using advanced technology and advanced physics insights to learn how to do computing better, quicker, more efficiently, and more powerfully. Okay, so that's a description of all of the different modules. Um, so I'll come back to the program structure now, just to refer to the part-time option. I just wanted to go through those modules before looking at this, because I think the easiest way to talk about the program structure for the part-time option is just to talk about what modules you will do. So basically, in the part-time option, you do about half of the modules each semester relative to the full-time program. So in year one, then, basically what we do in year one is do the modules on general relativity. So that's the semester one module on general relativity and the semester one maths module on partial differential equations, which is essential to understanding general relativity. Then in semester two, it's the two, let's say, advanced applications of general relativity to the study of black holes and gravitational waves. Year two, well, you do the remainder of the modules, and that means theoretical astrophysics, data analysis, and machine learning in semester one. And then in semester two, the high energy astro, the extragalactic astro, and high performance computing and quantum computing module. And it's in year two then that you undertake the summer project, which runs from May to August. For the part-time option, we want to make this as flexible and accessible as possible. So the lectures for the vast majority of the modules will be available remotely, and recordings of the lectures will also be available. So I think it's worth bearing that in mind, that this makes the part-time option more realistic. I think it's probably worth emphasizing that the part-time option does not mean that the classes take place in the evening. They take place in the afternoons on a small number of days per week, probably 2 days per week. All of the part-time classes will take place. They'll be in the afternoons rather than the evenings, but as I've just said, the lectures will be available remotely and recordings will be available. So this will, increase your capacity to undertake the part-time program while still working full-time. Program requirements, well, we look for students who have a primary degree. So in the Irish system, this would be NFQ level 8. So this is internationally an honours bachelor's degree in an area like physics or astrophysics or theoretical physics or mathematical sciences or applied mathematics, or a closely related field, for example, engineering. The key question that we look at there is, have you studied sufficient mathematics in particular and sufficient physics to enable you to enter onto the program? So there's information on the course webpage about that. And if you have particular questions about your background in terms of maths and physics, I'd be very happy to answer those. And we look for students who have the equivalent of a second class honours grade 1 award here in the Irish system. So that's 60%. And we can figure out how that translates into grade point average in different systems. Okay, let's say a few words about careers. Kind of two main bullet points, as you can see from the slide. So first of all, this is an excellent path to a career in research in the areas of astrophysics and relativity. So the program, this master's program, equips you, it prepares you in terms of knowledge and skills. So from an undergraduate program, it can be very difficult to move straight into PhD research in these areas. And so the master's program equips you with the additional knowledge and skills that you would need. Having a master's also makes applicants for research grants to fund PhD research much more competitive. In particular, here in the Irish system, PhD scholarships are available from on a competitive basis from the Irish Research Council or Taoiseach Éireann Research Ireland as it's now becoming. So with a master's degree under your belt, you have better prospects of being successful in that application. And indeed, in some European countries, you find that a master's program is a prerequisite for entering onto graduate research, onto a PhD program. So that's the first career option that I would say maybe a quarter or a third of our students have taken over the last 4 years. Um, the other career option is, well, let me say it's everything else. You've been, as I've mentioned, undertaking this program equips you with, advanced skills in computing data analysis. These are highly transferable. They're highly sought over by a wide range of industries, including information and communications technology, data analytics, engineering, banking, finance, business consultancy, even marketing as well. Different areas of business now are really leveraging data analysis skills to carry out their work. And a lot of our graduates have gone into, well, we have graduates who have gone into all of those areas over the last 4 years, like I say, leveraging what they've learned and the skills that they've equipped themselves with um, through that third leg of the program, while spending a year learning some really cool science. Okay, I mentioned a few moments ago that to me, I think one of the most interesting and exciting parts of the master's degree is the opportunity to do the research project. So this is a summer project, and you will have an individual supervisor who will come who will be one of the researchers from the Centre for Astrophysics and Relativity. So you're not working with another student, you're working on your own, and you have one individual supervisor who will help you through the project. This immediately gives you the possibility to work with your supervisor on a PhD funding application. Every year, so the Irish funding cycle applications go in October, which is of course, very close to the beginning of the academic year. But we're always very happy to talk to students straight away about submitting an application for PhD funding while you are on the program, so at the very beginning of the program. And also, we'd be very happy to work with students who've demonstrated their capacities after the program, maybe after you've done your initial research on this summer project, and you would like to stay on to extend that work or to go into a slightly different area. And everybody in CFAR is always on the lookout for good students to work with on PhD funding applications. Okay, so the summer project itself, I think I mentioned the key things that there's individual supervision, it's an individual project. Um, so the remainder of the slide just mentions a few different areas where the students have done their projects over the last few years. This starts up in May, and we have a selection process that begins earlier than that. We have a selection process that runs through the beginning of the second semester. So what happens is that all of the researchers in the program team will make project proposals. They give a title of a project and a short description of what the project will entail. We ask students to make their choices as to which one they prefer to do, and we encourage students to talk to the different lecturers about those projects. We usually have a session early on in the second semester where all of the researchers and all of the students get together, and the researchers will describe their different projects. So everybody does a very brief presentation about what projects are available, and the students can then make their choices. So some selection does sometimes need to be applied. In other words, not everybody will get their first choice of project, but over the years we've had the vast majority of students would get their first or second choice of project. Um, the selection, when we need to apply selection, it's on the basis of your first semester results. So everybody, on the very first day in September is aware of this, that there may be selection projects that kicks in second semester based on your performance in the first semester. Okay, so in terms of different areas, well, lots of different aspects of black hole physics, in particular quantum aspects of black hole physics, various studies of gravitational waves, typically propagation, interaction, geometrical properties of gravitational waves, the problem of motion in general relativity, which usually refers to the two-body problem in general relativity. This two-body problem is a lot more complicated in general relativity than it is in Newtonian physics. You can essentially study most of what we need to know about the two-body problem in Newtonian physics. This is two bodies rotating around one another, for example, a planet orbiting the sun or two neutron stars orbiting one another. In general relativity, this is an immensely complicated problem, and there's still active research going on that problem. So I mentioned already quantum fields in curved spacetime, studying things like Hawking radiation, the emission of quantum particles in the early universe or from black holes, and then my own area, mathematical relativity, um, studying the kind of hard mathematical problems that are thrown up by general relativity. And my particular interests there, I suppose, are around the mathematical problems that pop up when we study gravitational collapse, formation of black holes embedded, black holes in cosmological backgrounds, various problems like this. Under the astrophysics heading, again, a range of different possibilities there, studying astrophysical plasma, studying black hole formation, especially in the early universe, studying protoplanetary disks. So these are disks of dust and rocky matter that are the things that form before the matter coalesces to form a planet. And study of solar weather. So the sun is a star. So studying solar weather counts as astrophysics. Observations and characterizations of exoplanets, studying high energy astrophysics. So, in particular, looking at gamma ray and X-ray sources and looking at the science of two of the new telescopes that have come on stream recently that I mentioned at the beginning of the presentation. This is Athena and the Cherenkov telescopic array. Okay, so a wide range of different possibilities there. We're always very keen for students to suggest their own project areas, their own project titles. I'm very happy to work with students to allow them to pursue their own interests while undertaking their project. But this isn't something that students necessarily have to do. As I said, the supervisors propose project titles, and then we ask students to make their selections. Okay, so that brings us to the end, as you can see. Very happy to answer any questions that you have. You might want to put them in the Q&A now. You have my contact details there. My email address is the best way to contact me. I'm very happy to answer any questions that you have about the program. And for further information, very straightforward to find those further details about the program and about the application process. Just go to dcu.ie/DC742, or if you just Google DCU DC742 or Google DCU Astrophysics and Relativity, you'll find us there. Okay, thank you very much.
There is one question in Brian so
Yeah,
far, just about the program timetable and what it's
yeah,
like.
okay. Yeah, so I mentioned about the part-time program, um, and that we sort of squeeze all of the lectures into 2 afternoons a week. So if you've been watching and carefully the description of the full-time versus the part-time program, that leaves you, that's two of the modules take place over 2 afternoons. The other two modules, again, we do our very best to make sure those lectures are all in the afternoons, and it's at the very most 4 days a week. Um, this year we were able to squeeze the teaching into 3 days, and I think in the first semester we had to have one of the classes on a fourth day, but it's never more than 4 days, and more usually 3 days a week. And the number of lectures would be, so for each module you're talking about 3 to 4 hours, so it's in the region of 12, 13 hours contact hours a week. but it's it's I should say it's a really interesting program, but it's a challenging program. So it doesn't mean that your total time commitment is 12 hours a week. It needs, lots of work on the problem sets, on the tutorial questions, and the study of the lecture content, of course. Okay, so question there about the breakdown between exams and projects. Okay, so I think this question refers to what happens, how is each individual module assessed? So this is different for different modules. Um, so the project itself, of course, the main thing in the project is to write the report and to make a presentation about your report. So that's the summer project module. There are smaller elements to ensure that students are moving along, and we do some stuff on presentation skills and so forth. So the taught modules, let me call them that, the taught modules of the program would have a variety of assessments. Um, so typically this would involve a take-home work. I don't think anybody would be using in-class tests for their continuous assessment. So it's typically, I suppose you'd call it homework. So, but this is challenging stuff. So you'd have maybe over the course of the semester. So for my module, um, there's four problem sets that students are assigned roughly every 3 weeks. That's take home work. You get a week and a half to complete those. And then there's an exam at the end of the semester. And what we've all moved towards is something that emphasizes the importance of the continuous assessment. So this is where you have this is where you really need to spend the time learning how to say do the calculations in differential geometry, learning how to answer the problems that arise in these modules, and then the terminal exam would be maybe 50% of the module total, maybe down to 40, maybe up to 60, but that kind of ballpark. Um, the data analysis module has a higher project component that does have project work to be completed in it. But I suppose maybe the first thing I should have said is that it's different in different modules. Um, but um, typically with an emphasis on continuous assessment, take home work and project work. But most of the modules would have um, most of the modules would have a final exam as well. Okay, so the next question I see is about career opportunities after the course. Where are our graduates working? So I mentioned that there's kind of two routes that our graduates go. One is pursuing research, so um, working on a PhD applications, getting PhD placements, and carrying on in the area of astrophysics or relativity. So we have, I think, three of the graduates are currently doing graduate research studies here in DCU, or have indeed completed graduate research here in DCU. We have other of our graduates who are undertaking PhDs in. We have at the moment, we have graduates in the UK, in Germany. I think we've one in Sweden as well. Um, and people from the last year's class currently still working on applications, and indeed on this year's class working on applications to pursue PhD study elsewhere. So where else do they go? Well, the answer is everywhere. But in particular, because our graduates have developed, very strong skills in data analysis and in computing, a lot of our graduates would go into jobs that reflect those skills and that harness those skills. So working in information communications technology, graduates have gone into banking, into finance, and into uh, into companies where you wouldn't immediately expect somebody with a very technological background to be going into, but large manufacturing firms who are now using data analysis in, say, their marketing division, in their product design division, and in their product design division, where everybody now is using data, using machine learning, and so forth. Okay, so the English proficiency. Okay, I would have to look that up. Um,
I can come in on the English proficiency.
Yeah.
Um, so there is um, the English proficiency are all outlined on the website. So we do accept all the main tests, so TOEFL, IELTS, Duolingo. If you're doing one of the smaller ones like the Cambridge one, we accept them as well. There's a section on our website. If you just look up English Language Requirements DCU, it will give you all the listed scores. So, for instance, Duolingo is 120 overall with 110 in each subscore. IELTS is 6.5 overall with at least six in each subscore. And they're all listed there on the website for you to have a look at. One thing to note as well is you can apply without your English exam being done, and you can get a conditional offer, and then you can submit that English test at a later date if you do wish to do it that way.
Okay, yeah, I'm just having a quick look at the website, and you'll find it there. There's a link to the entry requirements, and then there's a link to actually here. I maybe can I put this link into
Yeah, you can
the
put it in the
Q and
chat
A?
there, even
Yeah.
to the chat, and that
Oh
should
yeah,
work
I'll put it in
fine.
the chat. That'd be better. Yeah. Um, okay, so hopefully you'll be able to follow that link, and that will bring you then directly to the GCU web pages where it describes the English language requirements for the program. Now, I think you also had a question there about the application fee, and again, I will defer to Frank on this. I think there's a there's a small application fee because, of course, this is work for the university to process applications.
Yeah, there
I
is a
think that
€50
okay,
application fee, which allows you to apply for three different programs. So when you're submitting your application through the portal, it will ask you to just pay that fee at the end of your application.
okay. How many people in the class? Yeah, the classes are small, so you get lots of attention from the lecturers. So we always have the opportunity. You'll always have the opportunity to, discuss any questions, discuss any difficulties that you're having with the material, either in class or afterwards. Um, so over the first 3 years of the program, I think our average numbers were around about a dozen students. And well, for us as lecturers, and I think for the students as well, this is a really nice number because there's enough people in the class that you can talk to. The numbers were a little bit lower this year, but the first 3 years we had about a dozen students. And what this means is that we can have these very interactive classes where students say, hang on a minute, I don't understand that. Can you go into that in a bit more detail? And you know a, a really interesting discussion can take off then, very different from having a class with 50 or 60 students where it's very difficult to pursue those kind of opportunities. So a good size, I would say. Yeah, so I think that's the perfect number. Round about that a dozen 15 students is a really good number, and like I say, in the first few years that's the kind of numbers that we had.
Great. Yeah, I think that's the end of the questions. I noticed a couple of people have joined late or towards the end. There will be a recording of the whole webinar distributed afterwards, some point today, for anybody that might have missed the start or certain sections. But thank you so much, Brian, for joining us and giving us a
Okay.
great overview of the program. And thank you to everyone that joined as well to tune in and listen. I don't know, Brian, if you have anything else before we wrap up.
No, no. Like I always say at this point, if you got any questions, just drop an email and be very happy to answer those. Or indeed, to set up a Zoom call if you want to have a bit more of a chat about the program, find out a bit more detail. But for now, we can leave it at that. Thanks very much, Frank, and thanks
Perfect.
to everybody for coming along.
Okay. Thank you, everyone.